Hey guys, so we're back on this 8.1 and we're going to do one more fun thing. So we're going to look at graphs that are not polynomials. So what's nice about when you're sketching polynomials, they'll have a maximum, clear maximums, they'll have clear minimum points. And the nice things about polynomials is that they're continuous for all reals. So all of these little guys are nice polynomials and they're continuous everywhere. So what I want to look at now is like what happens when you look at like weird guys that aren't polynomials and you have to find intervals of increasing and decreasing. So for example, like f of x equals 1 over x, okay? And so f of x equals 1 over x looks like this. And so he's decreasing for all real numbers, but like when you take the derivative, you're not really getting where your derivative is equal to 0 because at x equals 0, this function is undefined, right? But clearly there's something weird happening there. Or if you say look at g of x equals the square root of x, if you're looking at that guy, you're increasing for all reals, but like if you're looking anywhere less than 0, this graph is not defined, okay? Last but not least, I'll pull up this little guy, 1 over x squared. He's relevant because when we look at him, oopsies, we've got him increasing, and then at his vertical asymptote, he changes from increasing to decreasing. So you're going increasing on this side, he's decreasing on this side, but notice how there's no relative max here, right? Because my graph is not continuous or connected at that point. So when you're trying to describe the shape of these weird graphs, we just have to be a little bit more careful. All right, so let's attack one. So for example, let's find the maximum value. We want to find the maximum value of this graph. F of x equals x times 1 minus rad x. Okay, no calculator. So we got to get the max value. All right. So we know with maximums, you got to take the derivative. I would suggest distributing in first instead of using the product rule. So f of x is equal to, let's see, x times 1, which is just x. And then I'm really doing x times x to the 1/2, which is plus minus x to the 3/2. Nice. So now I've got to take the derivative of this little guy. 1 minus 3/2 x to the 3/2 minus 1 is 1/2. When we're trying to get maximums, the next thing we have to do is set them equal to 0. This looks scary, but don't get scared. I think you guys tend to like to solve things with radicals, so I'm going to make this 1 minus 3/2 rad x because something to the 1/2 is the square root. You can move that 3/2 rad x over to the other side if you want. And then I need to divide both sides by 3/2, which is the same thing as multiplying by the reciprocal, which is 2/3 times 1. All right, now to get x alone, I got to square both sides. So x is equal to 4/9. All right, and it feels like we're done. They said find the maximum value. What's nice is there is only one, so it is our maximum value because they told us there definitely is one. But we need the value, and when they say max value, they want the y value. All right, so how are we going to do this? We have the x, we got to sub in the y. So now we've got to find f of 4/9. Okay, so that's 4/9. I'm subbing into the original. 1 minus the square root of 4/9. Oh, shoot, and I don't have a calculator. I'm going to cry. No, I'm not. I'm going to enjoy these fractions because it's fun. 1 minus the square root of 4 is 2. The square root of 9 is 3. Oh, boy. That's 1/3, right? So the maximum value, it's teensy weensy, is 4/27. What? Oh, we got to investigate this. So sometimes they'll actually ask you about these guys using your calculator, which is cray-cray for me to think. But let's graph this original guy. What did we have? We have x times 1 minus the square root of x. What? Invalid input. Does it want a times here? Whoa, Miss Capola, that's a crazy thing. It needs the times. It doesn't just like parentheses. Now, I'm going to change this. Oh, I'm going to change my maximum to just, I don't know, 1. Because notice it doesn't even go any higher than 1. So look, he reaches a little maximum. Menu, analyze graph, maximum. I'm going to go to the left. I'm going to go to the right. Oh my gosh, 0.44444. That's 4 ninths. I wonder if 4/27ths, 4/27ths, what is that? 0.148. Guys, we got that. Isn't that fun? Yay, I loved that one. Cool. All right, so that was kind of fun. We didn't really have to stress about maximums or minimums or anything, or not maximums, or like looking at the domain of that guy. So let's just do one more. What if I give you, say, I don't know, f of x equals x squared plus 1 over x squared. And I want you to get the turning points, the coordinates of any turning points, maxes versus mins. So we know we have to take the derivative. Before I take the derivative, I'm going to rewrite him. X squared plus x to the negative 2. You should be able to take this derivative without me. It's a pretty straightforward one, and it would be even nicer if you could set it equal to 0 all by yourself. No one would be mad. So you've got a couple options here on how you can solve him. I'm going to actually factor it. I'm going to take a 2 out, and you have to take the least amount of x's. They each have an x, but the least amount that they have is negative 3. I know that feels weird. You have a couple of ways you can do this. I'll show you the other way as well. All right. When you are factoring, it's a fancy form of division. And when you are dividing, so really what I'm doing is 2x divided by 2x to the negative 3. Okay. Which is going to give me x to the 4th. And then something divided by itself is just minus 1. Okay. So when I set each of these pieces equal to 0, be careful. So this is really 2 over x cubed equals 0. And if you multiply both sides by x cubed, this will never happen, okay? But he is where my original function is undefined, right? X equals 0 is a vertical asymptote of the original function. And he actually will continue to be a vertical asymptote of the derivative. And I can prove it to you here if I rewrote this as this. See, he's a vertical asymptote. I could have even written him as 2x to the 4th minus 2 over x to the 3rd. And how did I get that? I multiplied this guy by x to the 3rd over x to the 3rd to make a common denominator. Anyway, all of these are equivalent. They're all equivalent. But it's important, even though this won't happen, he is still going to be a critical point. For the same reason that we talked about over here, that vertical asymptotes change from positive to negative. They don't have to, but you can also just, I don't know, be consistent. Sorry, I've been recording videos for a while now, and I'm just like kind of losing my mind. Hopefully I'm not torturing you. Okay, so I've got x to the 4th equals 1. I'm going to 4th root both sides. When you take an even root, remember to plus or minus. So my critical points that I'm going to put on this sign chart are going to be a little different. It's going to be negative 1. It's going to be 1. It's going to be 0. This is where my derivative is equal to 0, and this is where my derivative and my original are undefined. So I can even write, actually, I'm going to write that this is a vertical asymptote. It's a vertical asymptote of the original as well as the derivative. All right? And so last but not least, I got to sub in my test values. Remember that I said subbing in your test values into factored form is always best. So my test values I'll put up on the side are negative 2, negative 1/2, positive 1/2, and positive 2. Okay? And so again, we're going to come in here. Don't be scared. Oh boy. Don't be afraid of this. It's just saying you're essentially cubing it, right? So if I take negative 2 and I cube it, it's still negative times 2, still negative, right? Negative 2 to the 4th is a positive number that's bigger than 1. So this is going to be a negative, and so f of x is decreasing. Negative 1/2. Okay. I'm cubing negative 1/2. Still negative. Times 2, that's still negative. Now, Negative a half to the fourth power is a really little fraction, but he's going to be a positive little fraction. Minus 1, since that fraction is less than 1, it's going to be a negative. A negative times a negative is a positive, so I've got increasing. Okay? Now I'm going to sub in a half. This is positive. Anything to the third, a positive to the third. A little tiny fraction, minus 1, is going to give me a negative, so negative decreasing. Last but not least, I'm going to sub in 2. Positive, 2 to the fourth is bigger than 1, so a positive times a positive is a positive, which means it's increasing. So we can talk about our turning points here. We have turning points at x equals negative 1 and 1 only. Even though it goes from increasing to decreasing here, since it's a vertical asymptote, it's not a turning point. It needs to be continuous to be a turning point, okay? At negative 1, we're going from decreasing to increasing, so this is a relative minimum. And we're going from decreasing to increasing at 1 as well, so this is a relative minimum. And so you might be saying, Ms. Capoli, crazy cat, what does this look like on a graph? And I'm going to answer that right now. So let's get there. All right, we're going to do tab. Hey, tab. And we're going to delete our little friend here. And I'm graphing him. So let's see. X squared plus control divide 1 over x squared. Right. Ah. Okay. So sorry, the window was a little off, but let's see. I wonder, can I? Okay, so you can kind of see, yes, we've got ourselves a vertical asymptote here. And here are our minimums. We can kind of see them here at 1, negative 1, 2. And then let's see, the other one should be at regular 1, 2. All right, so that's kind of cool. We've got this fun little graph. Whoa, crazy zoomage. Sorry, I don't know what I did here. But we had this graph with our minimums at negative 1, 2 and positive 1, 2, which is exactly what we were expecting. And then you've got that vertical asymptote right there in the middle at 0. All right, so this was another fun activity. I hope you had fun. Talk to you later.